Okay, so in the last lecture, we saw the Haldane model, which is a model of electrons hopping on a honeycomb lattice like graphene, but with a gap, with a mass term, which opens a gap. And we saw that such a mass term could drive the system into two topologically distinct gap phases. One of them was characterized by a Chern number, which is 0, and the other one by a Chern number, which is non-zero. So what we didn't see is what is actually the physical significance of this topological quantum number, the Chern number. So our goal in this part is to derive the relation between a topological invariant, the Chern number of a band insulator, and a physical property, the Hall conductivity. We're going to derive the so-called celebrated TKNN formula, which is named after its four discoverers listed here. And what this TKNN formula states is that the Hall conductivity, sigma xy of a band insulator, which is gapped system, is equal to the quantum of conductance, E squared over H, times nu, which is an integer. And this integer nu is equal to the sum of the Chern numbers of all the filled bands of our band insulator. Okay, so it's a relation between a topological invariant, nu, and the Hall conductivity sigma xy. It proves that sigma xy in a band insulator is actually quantized. On the way to deriving the TKNN formula, we're actually going to also derive the semiclassical equations of motion of a Bloch electron moving in a periodic potential. And we will see how to derive from the semiclassical equation of motion the Hall conductivity sigma xy. Okay, so we're dealing with an electron moving in a periodic potential. And what we want to do is to derive semiclassical equations of motion to describe the motion of this electron. And to do that, we need to start from a wave packet. So we want to not work with Bloch waves, which are completely extended, but construct a wave packet that has a reasonably well-defined both momentum and position, although of course they cannot be perfectly well-defined at the same time. Our goal now is to derive an expression for the average position of an electron in this wave packet state. We do that as usual by writing the integral over dr of r times mod of psi squared. And we can express this by hitting the exponential factor here by a k derivative that would bring down a factor of r, and then integrating by parts over k. Okay, and if we do that just in a couple of steps, we would get to this expression that has two terms. The first term is the k derivative of the envelope function f of k. This is what you might expect if you recall that usually in quantum mechanics, the position operator is I times d to dk of the wave function in k space. And the second term is a mod of f of k squared times this a factor a of k, which is related to the k derivative of the Bloch wave function. And we can rewrite this in this nice compact form. It's the average or expectation value with respect to f, the envelope function of I d dk, plus this extra factor a of k. And what is a of k? Explicitly, a of k is written in this form. It's I times the integral dr, u star, the Bloch wave function, d dk of u of k. This is actually an object we've encountered before in the course. This is the so-called Berry connection of the Bloch wave functions. And this combination, I d dk plus a of k, reminds us of gauge invariance. This is a covariant derivative with respect to k. And we can understand where this form actually comes from. We know that if we change the gauge, okay, basically multiplying the Bloch wave function by an arbitrary phase function, but at the same time, we also multiply the envelope function by the inverse of this phase, the actual wave function did not change, and therefore the average position could not change either. And this covariant derivative form guarantees that the average position does not depend on this choice of phase theta k. Okay, so just to get a better feel for this expression for the average position, let's take a simple example. So let's imagine that our envelope function f of k is actually just constant over the entire Brillouin zone. That's not a wave packet with a well-defined momentum. It has ill-defined momentum, but relatively well-defined position. So then we can insert this envelope function into this expression for the average position. The first part, df dk, is 0. So we simply get the integral over the Berry connection, a of k, over the entire Brillouin zone. This is an expression we actually saw before in the course. This is nothing but the polarization or the average position of a Wannier wave function. This is a wave function that spans the whole band and is localized in space. So here's in white our periodic potential, and in yellow is a particular Wannier wave function which is localized in a certain lattice site, and the integral over a of k is nothing but the average position of an electron in this Wannier state. What happens if instead of a constant for this envelope function we choose this phase function e to the I kx times a? We see that all that changes is that now this derivative of f with respect to k is going to pick up another factor of plus a. So the Wannier function simply shifts by one lattice spacing. All right, so now back to a wave packet. We're going to put our electron in a wave packet and ask about the dynamics when we apply a weak electric field. So here's our periodic potential again, and we want to apply an electric field in some direction, say in the plus x direction. One way to represent this electric field is as a tilt of the potential in which the electron moves, but that's not a particularly convenient gate choice. There's a more convenient gate choice, which is choosing representing the electric field in terms of a uniform in space vector potential. And then, as we know, the electric field is equal to minus the time derivative of this vector potential. The advantage of this gate choice is that the system is still translationally invariant even in the presence of an electric field, but now the Hamiltonian of the system became time dependent. Okay, so how do we deal with such an electric field? So as we know, the way it enters the Hamiltonian is via a minimal substitution. The Bloch Hamiltonian h of k simply becomes h of k plus e, the electron charge, times a of t, the vector potential as a function of time. Okay, and we can define the gauge invariant or kinetic momentum k tilde, which is simply this combination k over k plus ea. So this is k tilde, the kinetic momentum. And we see that the derivative with respect to time of the kinetic momentum is simply equal to the force minus E times the electric field E. Okay, so just to visualize, this is what the dynamics of our wave packet would look like in the presence of an electric field. So suppose that we start from our wave packet in some kinetic momentum, k tilde, and we apply an electric field. The center of mass momentum of this wave packet is simply going to shift or drift as a result of the application of the electric field. Just as we expect, we apply the force, so the momentum of the particle changes. So now we're going to take into account the fact that the electric field we're going to apply is very small. Ultimately, we're going to be interested in linear response of the system, so the electric field is infinitesimally small. And what this means is that the momentum of the particle is changing very, very slowly in time. So this means that the evolution of our Bloch electron is actually adiabatic as a function of time. So here's what it looks like. This is a cut through the dispersion in momentum space. And suppose our initial wave packet is concentrated near this momentum. Now we're applying a very small electric field, so k tilde, the kinetic momentum, is changing very slowly in time. But as we know, because of the adiabatic theorem, if it started uniquely in the lower band, it's going to track the lower band as a function of time and never transition to the other band. So at the end of this process where we turn off the electric field, it just shifted to a different momentum, but stayed in the same band. And moreover, if our electron started from a certain Bloch wave function, we know how this Bloch wave function would evolve in time using the adiabatic theorem. So we know that the wave function uk of r and time t is just going to be equal to the wave function u of k tilde of t, meaning simply the corresponding Bloch states in the shifted momentum k tilde after time t, times a phase, which is equal to the sum of two terms. The first term is the dynamical phase, which is the integral over time of the instantaneous energy epsilon of k tilde of t. And the other term, as usual, is the Berry phase gamma of t. Gamma of t is equal to the integral of the Berry connection A of k dot dk, or we can also express it as an integral over time dt prime A of k tilde of t prime times the time derivative dk tilde to dt, which is related to the force or to the electric field. Okay, so we're actually dealing with adiabatic evolution of Bloch electrons. Now we can ask, what is the dynamics of our wave packet? Okay, so here's our wave packet again. So we have our envelope function f of k integrated over k. And here what we used to have is e to the I k dot r times the periodic part of the Bloch function uk. But now we evolve each one of these Bloch wave functions adiabatically with time. So basically what we have is what we called before uk of t, which is evolving adiabatically. It's tracking the Bloch wave function as a function of momentum and gaining the dynamical phase and the Berry phase. Okay, so now we can identify this factor as our time-dependent envelope function fk of t. In terms of this time-dependent envelope function, this is the time-dependent wave function of our wave packet. It's just fkt times the instantaneous Bloch wave function. And we can find the ith component of the average position of this wave function using our formula from before. So in terms of the envelope of the time evolving envelope function fk of t, it has two parts. One is the expectation value of I ddk in this wave function envelope function fk of t, and the other one is the average of the Berry connection in the instantaneous momentum k tilde of t. Okay, and that we can express simply by inserting the expression for fk of t and taking the derivative with respect to k. We can express in this form. So the instantaneous center of mass position of our wave packet is equal to its position at time equals 0 plus this integral over k that has a few contributions. This contribution is coming from the dynamical phase, the derivative of the dynamical phase with respect to k. The other part is the derivative of the Berry phase with respect to k. And the last part is the Berry connection A. Okay, so we have the position of the electron. We simply take the time derivative and we find the velocity of this wave packet as a function of time. So there are a few steps here. I won't show them in detail. You can find them in the attached document, but they're straightforward. And you just take the time derivative, and this is what you get. Okay, so this is the average over k, the envelope function fk squared, times two terms. The first one is d epsilon k dk. This is just the usual group velocity of a wave packet. And the second term is minus e times the time derivative of the vector potential, which we identify as the electric field, times this combination of derivatives of the Berry connection with respect to k. Now notice that here I've used the Einstein summation convention. Every repeated index is summed over. I and j are equal to x and y, the two spatial coordinates. Okay, and this combination of dAj with respect to ki minus dAi with respect to kj is starting to look like a curl, and you can play with that a little bit and see quite easily that this indeed can be expressed in this compact form. So there are two terms again. One is the group velocity, the epsilon k dk, and the other one can be expressed as minus e times the electric field. Okay, A dot is related to the electric field, a vector product with this quantity B of k, which is the Berry curvature. That's the curl of the Berry connection with respect to k. Okay, so we've encountered this definition before earlier in the course. B of k is the Berry curvature, which is the curl of A of k with respect to k. And in terms of the Bloch wave functions, that can also be expressed in this form. It's the overlap between dkx of the Bloch wave function uk with dky of uk. Okay, and then taking the imaginary part of that. And then finally, if we want the semiclassical equations of motion, we simply imagine that our wave packet is very tightly confined in k, such that our electron almost has a well-defined momentum, such that the envelope function goes to a delta function. Okay, so now this average over k can be replaced by simply the value of these two functions of k at the maximum of our wave packet. So our electron now has both a well-defined momentum and position. And what we obtain is the semiclassical equations of motion of Bloch electrons. So these are the full equations of motion for both the momentum and the position. K dot, the derivative of the momentum, as usual, has two parts. One is the electric force, minus E times E. The other part we didn't actually discuss, but it's still there. This is the Lorentz force. So far, we've dealt only with the case where B, the external magnetic field, is equal to 0. And the part we've derived here is the equation of motion for the position. And this is the velocity r dot of our Bloch electron, which is composed of two parts. One is the group velocity, d epsilon k to dk, and the other one is the so-called anomalous velocity. So this is the new part that comes from the fact that this is not a free electron. It's actually an effect of the band structure of the electron, or more precisely of the Bloch structure of the Bloch wave functions as a function of k, and that's equal to k dot, the derivative, the time derivative of the momentum, a vector product with B of k, which is the Berry curvature. Okay, so the Berry curvature is given here. We can make one more step to expose the fact that these equations of motion have a nice symmetry between r and k. We can write the electric force as the gradient of a potential, or as the gradient of an energy, which is dependent on position. And once we substitute that, we see that these equations satisfy a nice exchange symmetry between r and k. Okay, so what is actually the content of these semiclassical equations of motion? So here they are again, and let's focus on the case where B is equal to 0. There's no external magnetic field, only electric field. And we can track what happens both to the kinetic momentum and the position of our Bloch electron. So here's B equals 0. So we apply an electric field. The momentum of the particle is drifting along the electric field, and the position is also changing, and it's changing as a result both of the group velocity and the so-called anomalous velocity. And notice that the anomalous velocity is actually perpendicular to the direction of the electric field, because it's, k dot is essentially proportional to E, and this is a vector. This is a vector product. B is the Berry curvature, which is always perpendicular to the plane of the motion. So as we apply an electric force, say in the plus x direction, the kinetic momentum is changing along x, and the position has the velocity has two components. One is along the direction of the electric field, but another is actually perpendicular to it. So the electron is actually going to deflect at an angle to the direction of the applied electric field. Now notice that this is quite unusual. So we didn't apply any magnetic field, and nevertheless there's a sideways motion of the electron. There's no cyclotron motion. This is just a result of the Bloch wave functions themselves. Having derived the semiclassical equations of motion, it's actually very easy to derive the Hall conductivity of the entire system. So we know how a single electron moves, and it's a non-interacting system. So we use our semiclassical equations of motion for the case b equals to 0. So we can just substitute k dot with minus E over h bar. So this is the equation of motion for the velocity. And here's our system. So our system is a band insulator. So we imagine a system with some number of bands, and all the bands up to here, the chemical potential potential are filled. So basically, all the states in the bands below mu are occupied, and all the other bands are empty. And what we want to do is to calculate the conductivity, meaning the current, as a function of the electric field, linear in the electric field. So this is the current operator. It's simply minus E times the averaged velocity of all the occupied states. So we integrate over k times n of k, which is the occupation number of the state at k, okay, which is 1 for any filled state and 0 for any empty state, times r dot of k, which is the velocity of an electron at that particular k. Okay, so now we simply substitute, and we see that the first term, the group velocity, is actually going to give us 0. Okay, why does it give 0? Because for an empty band, clearly it's 0 because n of k is equal to 0, whereas for a filled band, n of k is equal to 1, but then we integrate the gradient of epsilon k over all k's, and because it's an integral over a total derivative, that gives 0. So actually the only contribution for a band insulator comes from the anomalous velocity term, which is proportional to the electric field. This is what we expect. If we don't apply any electric field, we don't get any current. So this is the result. We simply pull out the electric field. So it's E cross Z, which is the direction of this vector bk, whose magnitude is the Berry curvature, times E squared over h bar, times the integral d2k times n of k, the occupation number, times the Berry curvature b of k at that particular k. Okay, so and from here we can actually identify sigma xy. So this gives us that the current is perpendicular to the direction of the electric field. So this is a Hall conductivity sigma xy. Okay, and we can read off the value of the Hall conductivity sigma xy. So sigma xy is equal to E squared over h times the sum over all the filled bands n, and each filled band contributes a number nu n, which is the integral over the Berry curvature. And as we saw earlier in the course, the integral over the Berry curvature over an entire band is actually equal to an integer times 2 pi. Okay, so this nu n is actually a topological quantum number, which is integer valued. So that's it. This is the TKNN formula that relates the Hall conductivity to the Chern number. We've derived it using the semiclassical equations of motion. So a couple of comments just before we end this video. One is one might wonder, okay, so we've derived a quantized Hall conductivity. What is actually the relation of this quantized Hall conductivity to the quantum Hall effect, to the integer quantum Hall effect that we saw earlier in the course? So on the face of it, these problems look very, very different from each other. In the quantum Hall effect, we didn't have a lattice at all. We didn't have a periodic potential. We just imagine 2D electrons that are moving in the presence of an electric field, and they form these, semiclassically, they form these cyclotron orbits. Okay, and there are no bands. But it turns out that this phenomenon of the integer quantum Hall effect is actually closely related to the phenomenon we've just discussed. It can actually be understood in the very same terms. Okay, I won't go into details of that, but the way to relate the two problems is the following. We just say, let's imagine that there's actually a very weak periodic potential that these electrons, in addition to the magnetic field, these electrons are seeing. Okay, so if you like, you can turn on an actual periodic potential and then take the limit where the strength of this periodic potential is 0. Okay, and we choose this periodic potential in such a way that the total flux of the magnetic field, which is going through a single unit cell of the periodic potential, is exactly phi naught, the flux quantum h over E. So this is the area of a single unit cell of this fictitious periodic potential, A unit cell times B, the magnetic field, is equal to phi naught. Now, as you know, if you have a uniform system in a magnetic field, translations in the x and the y direction don't actually commute. But if you define a unit cell such that there's a single flux quantum per unit cell, then the system has a discrete translational symmetry where translations in the two directions actually commute with each other. Okay, so we can define a new periodic problem, just like in a crystal, Bloch wave functions and Bloch bands, just like any problem in a periodic potential. And what are Landau levels? Landau levels are simply the bands of this new problem with a fictitious periodic potential. Okay, so these are the bands which are completely flat. These are Landau levels. Okay, so we can actually understand the properties of Landau levels using the very same formalism we used for band insulators, with one difference, that in this case the Landau level dispersion is exactly flat. Okay, and as you know, if you apply an electric field of an electron which is seeing a perpendicular magnetic field, this electron is going to drift in a direction which is perpendicular to the electric field and also perpendicular to the magnetic field. You can understand this drift motion simply as the anomalous velocity of an electron which is moving in this kind of band structure. The TKNN formula reveals the possibility of a new effect, the so-called quantum anomalous Hall effect. So we saw that you can understand regular Landau levels of electrons in a magnetic field using the TKNN formula, but there's actually another intriguing possibility. You can get a quantized non-zero Hall effect even in the absence of any external magnetic field. And this is what the quantum anomalous Hall effect is. The anomalous Hall effect, the fact that you can get a Hall effect without an external magnetic field, has been known for a long time. But the fact that it can actually be quantized has been discovered only relatively recently. So what is a quantum anomalous Hall or a Chern insulator material? So it's some kind of ferromagnet. So it's a system that breaks time reversal symmetry spontaneously. That you have to do. You need to break time reversal symmetry in some way to get a non-zero Hall conductivity. So imagine, for instance, a ferromagnet, and this ferromagnet is a band insulator. So there's some number of filled bands and some number of empty bands, and the filled bands have a non-zero Chern number, such that overall the system has a quantized Hall conductivity by the TKNN formula. And that implies in particular that if we put the system with open boundary conditions, there would be chiral edge states running around the boundaries of the sample. So as usual, in the quantized Hall effect, the bulk has a finite gap, but at the edge there would be chiral edge states. So sigma xy is quantized and non-zero even in the absence of a magnetic field. Okay, and this is what the spectrum of this such a system would look like. So as a function of one of the components of a momentum, say kx, there are multiple bands. Say the simplest example, like the Haldane model, there are two bands, and these bands have a non-zero Chern number. Say one has a Chern number of +1 and the other one has a Chern number of -1. And in the bulk between these two bands there's a finite gap, but at the boundary there's a chiral edge state which is running around the boundaries of the system. So there were a few real systems that are actually discovered to have this property, that are insulators and break time reversal symmetry spontaneously and have a quantized Hall conductivity. Maybe the best known example is very recent in twisted bilayer graphene, which is a system that we'll talk about later in this part of the course. At the particular filling factor of the lattice, the system actually breaks time reversal symmetry spontaneously and forms a quantum anomalous Hall state with a quantized Hall conductivity sigma xy, which is equal to E²/h. Now, you might think that the reason for the non-zero Hall conductivity is simply that the system is a ferromagnet, and this ferromagnet is creating its own magnetic field, and this magnetic field is responsible for the non-zero Hall conductivity. This is actually not true. So this is a good example. In twisted bilayer graphene, if you try to estimate the magnetic field that the ordered moments themselves are creating, it is actually negligibly small, and moreover, it actually goes down like the inverse of the system size. So if the system is a few microns, that will be a tiny magnetic field. On the other hand, sigma xy is equal to e² over h, and if you try to estimate the actual magnetic field you would need in order to get that Hall conductivity in the given density, that would be a huge field. This would be many tens of Teslas. So this is really something unusual. The Hall conductivity is not coming from an actual physical magnetic field. It's coming from the Berry curvature, which is a property of the Bloch wave functions of the system itself. Now, one extra comment: when do Bloch bands actually have a non-zero Berry curvature, and therefore might have also non-zero Chern numbers? So that is a microscopic property. It depends really on details of the system, but most importantly, it's a consequence of symmetry. So the system would have to break certain symmetries in order to have a non-zero Berry curvature. And once these symmetries are broken, there's no reason not to get a non-zero Berry curvature. So to get the Chern number, which is the integral over the Berry curvature over the entire Brillouin zone, for instance, you have to break time reversal symmetry. So just to wrap up, in this video, we've derived the TKNN formula, which relates the Hall conductivity of a band insulator to a topological quantum number, which is the Chern number of the filled bands. And on the way, we've actually derived the semiclassical equation of motion for Bloch electrons in the presence of an external electric field, which includes the so-called anomalous velocity, which is a sideways drift velocity perpendicular to the applied electric field, and the quantum anomalous Hall effect can actually be understood as a consequence of the anomalous velocity of Bloch electrons. So see you in the next video.